Hello everyone, can you hear me? I would like to change gear a little bit from galaxy cluster to star cluster, globular cluster. So as has been already shown from Florence talk on Wednesday, that for, modeling globular cluster is extremely challenging. So the challenge mainly comes from this huge dynamical range that need to be covered in cosmological simulations, from the cosmological scale all the way down to the scale of GMCs with the parsec scale, where the star cluster and the globular cluster form. But why do we need to take such a great effort on modeling globular clusters, modeling this sort of boring spherical object? So the answer to this question from Florence is because it's fun. Yes, it's fun, and I totally agree it's a lot of fun. But there's increasing observational evidence on the connection between this globular cluster system and their host galaxy. We know in general that globular clusters form at very high redshift, and they are typically metal poor. But I would like to emphasize here that they are indeed metal poor, but they are not metal free. For example, here I show the metallicity distribution of a galactic globular clusters. And you can see that the metallicity span a large range from -3 all the way up to 0.5. This means that these globular clusters definitely form at different epochs, and they may follow tightly with the metal enrichment history of our Milky Way. And another very striking observation is a tight linear correlation between the total globular cluster system mass and the mass of their host galaxy, host halo system. And this linearity may give us some hint that the globular cluster formation may follow well with the halo assembly history. And maybe in the future, we can use the globular cluster as a probe to trace back the halo assembly at high redshift. But before doing that, we need to answer the simplest question: how are globular clusters formed? So typically, there are two ways of doing it. One way is to construct a semi-analytical model, or a semi-analytical model or some analytical prescriptions to sample globular clusters in cosmological halo merger trees or some pre-existing hydrodynamic simulations. This kind of method will be talked about extensively in the next talk by Nick Choksi. The advantage of this method is that it is a pretty computational cheap, and it can sample a large number of globular cluster systems from different types of galaxies. The drawback is that it relies heavily on the assumption of the model. And another very promising result is from this Florence talk, that they use extremely high spatial resolution simulations to try to resolve the globular clusters at high redshift with thousands of stellar particles. And this is very promising, but you can already see the difficulties here, because they can only run the simulation to redshift 9. And it's very hard to construct the globular cluster populations along with cosmic time. So here I would like to try to propose another method, is to try to simulate globular clusters in cosmological simulations, but with star formation prescriptions that use individual star particle to represent individual star clusters. So what we do now, in our prescriptions, we form the seed of the globular cluster at the density peak of the star in the simulation. And then we grow this seed star cluster particle by accreting the ambient material around the individual star clusters. At the same time, we operate the stellar feedback simultaneously, so that this feedback will disrupt the ambient material of these GMCs, and eventually the feedback from its own stellar cluster will disrupt this natal GMC, and then this accretion will be terminated. Then the final mass that is obtained from the individual star clusters can be a good representative of the star clusters that are formed from individual GMCs. To do this, we do need to roughly resolve the GMC in the cosmological simulation. Therefore, we need a roughly kind of high resolution in cosmological simulations. So in our fiducial run, we do the 3 to 6 parsec resolution in cosmological simulations, and we run our simulation. So we test our simulation on the cosmological simulations of Milky Way-sized galaxies, and we implement these algorithms in R with this very relevant physical ingredient that I won't go through in detail. So the star cluster will accrete its mass from its central cell as well as 26 neighbors. The accretion rate is determined by this equation, which is controlled by this epsilon freefall parameter. It's the star formation efficiency per freefall time. And we include the stellar feedback processes from supernovae, from stellar wind, from radiative pressure. So one thing that I would like to first test is to see whether the simulation can reproduce the global property of the Milky Way-sized galaxy roughly correct. So we compare the star formation history of our simulated galaxy and compare it with the abundance matching result. We find that the stellar feedback from our star cluster particle can suppress the star formation rate at high redshift and roughly reproduce the abundance matching result. And we also check the properties of the newly formed young massive star clusters in the simulation. And we find that in our simulation, it is the massive cluster formation is an environment-dependent process. What do I mean? So this is the correlation between the star formation rate surface density and the maximum mass that can be formed in these different patches of the galaxy in the simulation. We find a strong correlation between the star formation rate surface density and the maximum mass that can be formed in the simulation. And also, there's an increasing rate between the star formation rate surface density and the cluster formation efficiency in the simulation. And these trends are consistent with observations of young massive star clusters that have been observed in the nearby galaxies. We also studied the cluster initial mass functions. We find in general, our model clusters follow a power law distribution with some exponential cutoff, and the power law slope is around -2, but it has a scatter between -1.5 to 2.7. We also find a very interesting result that there's a systematic difference between of this cluster initial mass function during major merger and the non-major merger case. So in the non-major merger case, the slope is a little bit steep. This means that it is less likely to sample to form more massive star clusters in non-major merger case. However, during major merger, the slope of the power law slope is a little bit shallower, and this will push the simulation. This will push this mass function to form more massive clusters that can potentially be the progenitors of global clusters. To see this trend or these effects more clearly, here I show the distribution of the formation time of all massive clusters with mass larger than 2 times 10 to the 5 solar masses. And you can see this distribution has a distinct peak. And so unsurprisingly, so these peaks are just coincident with the major merger events that are experienced by this galaxy. And this means that the major merger can strongly trigger the formation of the most massive star clusters that can potentially be converted into globular clusters that we observe at a low redshift. And then we follow the orbits of individual star clusters. We find that the star cluster first form at the density, at the very dense clumps at the center of the galaxy, and then it gradually migrates to outer orbits. So the cluster orbit is first preferentially tangential, but then as the orbital migration, it becomes more and more radial. And here I show the evolution of the galactocentric radius of one representative star cluster in our simulation. We find this orbital migration is quite clear, and more interestingly, so there are some spikes that you can see that at a very small amount of time, it changes the orbit changes radius dramatically. And these are also coincident with the major merger events. So here's the movie that shows what is going on. So these are the last major merger events that experienced by the galaxy. And you can see that there are a group of star clusters that are pushed pushed up to the higher orbits, and then they gain this orbital energy, and after that, the orbits of this star cluster become higher and higher. So this has dramatic effects on the following evolution of the globular clusters, because we know that in the halo, the tidal disruption is less violent than for the clusters in the disk. So this way, the star clusters may avoid some strong tidal disruption. So talking about this tidal disruption, we also calculate the evolution of the tidal field for individual star clusters, and by evaluating this maximum eigenvalue of the tidal tensor around each star cluster at different time. What we found is a strong decrease of this tidal disruption as the star cluster ages. So this is and initially the value of the tidal intensity is extremely high. It's about 2 to 3 orders of magnitude higher than the value that we evaluated as solar neighborhood value. And this means that the tidal disruption is extremely strong when the star clusters is just formed within a gigayear, when this cluster is not able to escape to the halo area. And once they are escaped out to the halo area, the value of this tidal intensity drops, and they are more likely to survive. And we calculate the tidal disruption rate and also the mass loss rate of individual star clusters in our simulation based on this prescription, and this prescription is calibrated from this n-body model of individual star clusters. And what we find is that the initial power law-like mass function for the star clusters can be transformed to a log-normal distribution, which is consistent with the current mass function of the globular clusters that we observed in the Milky Way and other extragalactic globular cluster systems. These have a strong implication that these young massive clusters that are formed at high redshift can be a good representative, can be a good candidate for the progenitors of globular clusters. We also have the metallicity information of these star clusters. For example, here I show the metallicity distribution of the survival star cluster in our simulation. And first, we find a broad range of metallicity from -3 all the way to -0.6. We also find that the majority of the star clusters that have a metallicity around -1.3 are disrupted. So this is very interesting, and we dig into the properties of these star clusters, and what we find is that these clusters are formed at the center, always formed at the central part of the galaxy. And they are they experience extreme tidal disruption. And also, because they are formed at the center of the galaxy, because of the metallicity gradient of this cluster, these clusters tend to be more metal-rich than their peer that are formed at the outer part of the galaxy. So these type of globe clusters are preferentially disrupted in our simulation. And also, we have the clusters, model clusters that are distributed in this metallicity and age plan. And we find a general agreement between our model global clusters and the global cluster population in our Milky Way. But we are lacking this metal-rich part. One reason is that although this type of simulation is computationally cheaper than the one runs by Florent or Kim, they're still expensive. We have this 3 to 6 parsec resolution, so the simulation stop at about redshift 1. But we may expect that after redshift 1, there might be some young massive star clusters that can be formed that can fill the gap of this metal-rich subpopulation. And I think that's the summary. I'll take some questions.
What was the dark matter particle mass in your simulations?
Dark matter particle mass is about 5 times 10 to the 5 solar masses.
I worry that this is very similar to your globular cluster mass, so that you could have two-body scattering dominating your ejection.
So the Hydra Simulator, the gravitational solver is done at the root cell level, and then it uses the relaxation method to calculate the potential. So basically, we treat the dark matter particle as this smoothing gravitational field. So it's not that is not an issue. But there might be some issue for the dynamical friction of the star clusters.
More questions? Okay.
Hi. I was just wondering, so a lot of these models that stress how important it is to kick the globular cluster out into the halo say that while it's in the disk, it can be tidally shocked by like neighboring GMC clouds, and that can be very disruptive. But I think, as you mentioned, even after it gets out of the halo, it still passes the disk and gets like tidally shocked. So isn't that, I just always found that a little confusing, the models that say that the most destructive thing is tidal shocking by GMC, and once you're in the halo, you're fine, because you still get tidally shocked by the disk. So what do you have to say?
Yeah, so this is actually one of the uncertainties of calculating the disruption of GMCs because of the tidal shock. Well, so we have this very high time resolution to resolve these tidal shocks. And what we find is that these tidal shocks can be very strong when the globular clusters that penetrate into very deep of the gravitational potential of the galaxy. And to evaluate the effects is very tricky. So one thing is that it is very sensitive to the assumption of the radius of the globular clusters, which we don't have any information on. So this, this can be another thing that needs to be explored by the n-body models.
What's the halo mass and the stellar mass at the last redshift?
So it's the Milky Way sized galaxy.
Yes.
It's about 2 times 10 to the 11 solar masses for halo mass at redshift 2. At the redshift 1.
How about the stellar mass?
No. That's halo mass. Halo mass, sorry. Halo mass.
And how about the stellar mass?
That's a good point. We checked the stellar mass halo mass relation, and it's basically lies, especially from redshift 5 to redshift 1, it lies at the stellar mass halo mass relation from the old Biruzzi paper. Okay. But not the new universe machine Biruzzi paper.
Okay, I'd like to thank the speaker again.